Please turn to page 35. These three problems are going to be your warm-up. Fill in the degree, the zeros, and the end behavior, and then we will do the rest of it together. So we're going to pause the video here for you to do that. We'll give you about 3 to 4 minutes. Okay, I zoomed in a little so I could write more legibly. The degree of number 1 is 1. It's the highest exponent. And the 0 is going to be -1. That's the x-intercept. Because the degree is odd and the leading coefficient is positive, I know that as x goes to infinity, y is going to go to infinity for right end behavior. And as x goes to -infinity, y is going to go to -infinity. So I'm going to plot my x-intercept and fill in with my end behavior. So now for number 2, the degree is 2, but the x-intercepts are still -1. And because it's an even degree with a positive leading coefficient, I know for the right end behavior is going to go to positive infinity, and the left end behavior is still going to go to positive infinity. So I'm going to plot my x-intercept, and then I'm going to find some other nice points. I know the end behaviors are going to go this way, but if I plug in 0, I'm going to get +1, and it's a parabola, so I know there's the symmetry. So there is the rest of that parabola. And then for number 3, for x plus 1 cubed, excuse me, our degree is 3. We still have a 0 of -1. And it has the same end behavior as number 1 because of the odd degree and the positive leading coefficient. Oops, I can't fit that. So I'll plot my 0. And then this is x plus 1 cubed. So if I want to get some nice points, if I plug in 0, 1 cubed is 1. If I plug in 1, 2 cubed is 8. Up here. And I remember that cubics and cube roots are symmetrical, so I can go this way as well. So if we plug in -3, we're going to get -8. It's hard to count on this small grid. 1, 2, 3, 4, 5, 6, 7, 8. Right there. And we get this increasing graph. I missed my point. Let's see if I can do that better. Almost. Good enough. Okay. So now the next question is, what do you notice and what do you wonder? That's pretty open-ended. So let's talk about some key vocabulary here. When the degree is 1, you can see that the x-intercept intersects and goes through the x-axis. So I'm just going to write crosses x-axis. But over here where the degree is 2 and there's only 1 0, our graph is considered a double root. This 0 is used twice. Like if I write out the factors as x plus 1 times x plus 1, you can see that the root of -1 is there 2 times or twice. So this is called a double root. And when you have a double root like that, the graph is going to be tangent to the x-axis. And if you think back to geometry, when you had a circle and a tangent line, it just skimmed the circle. Well, that idea of tangent is the same thing. It just skims the x-axis. It touches it and turns back around. Now, when we have a degree of 3, and we have the repeated zeros, this is a special point called the point of inflection. And the point of inflection is where the concavity of the graph changes. And now we have to define that. So for this x plus 1 squared graph, the whole graph is considered concave up. So concave up is up like a cup. So the curvature is up. Where now if you look at our x cubed graph, or x plus 1 cubed, from the x-intercept to the right is concave up. It's curved up. Whereas over on the left side of -1, when x is less than -1, the graph is curved down, and that's called concave down. So over here, the graph is concave up, and over here on the left, the graph is concave down. And the point of inflection is where the concavity changes, where the curvature of the graph changes. So at the x-intercept, here at -1, the curvature changes from being curved down to curve up. And we're going to use this vocabulary of tangent and concavity and point of inflection as we go through our lesson today. Okay, without graphing, write the required characteristics of the polynomials and then sketch the graph. Okay, same idea. Let's look at number 5 together, and then you're going to do 6 and 7. In number 5, if I want the degree, I'm going to think about what the highest exponent would be. So we have a degree of 1 here and a degree of 1 here, so that makes a degree of 2 total. The zeros are when each factor equals 0, so that's -1 and 2. And since the leading coefficient is positive and the degree is even, for n behavior for the right, as x goes to infinity, y is going to go to infinity. And as x goes to -infinity, y is also still going to go to positive infinity. So for our graph, we know we have a 0 at -1 and a 0 at 2. It's quadratic, so we're going to get a parabola. Okay, we'll pause the video here. For 6, try just the degree, the zeros, and the end behavior, and then we'll go over the answers before we graph and do 7. The degree in 6 is going to be 2 plus 1 more for 3. The zeros are going to be -1 twice because of that squared, and then 2. So when you graph the -1 twice, well, we can't. You can only plot that point one time. But our end behavior, because it's an odd degree, is going to be as x goes to infinity, y goes to infinity. And as x goes to -infinity, y is going to go to -infinity. So if you think about an odd degree with a positive leading coefficient, so the only way to get up to infinity on the right and down to infinity on the left is to be if we just skim the x-axis at -1, where we have that degree, we have that repeated 0. So we're going to touch the x-axis there and then intersect it at x equals 2. Okay, we're going to pause the video, and I want you to try all of number 7. We'll give you 3 or 4 minutes, 3 minutes to try that. Okay, the degree is going to be 4. 3 for this 0 and 1 for this factor. I'm going to rephrase that. 3 for this factor and 1 for this factor makes 4 total. The zeros are -1 and 2. So again, it's the same roots as the other 2 graphs. Now, because it's an even degree and positive leading coefficient, I know both end behaviors are going to go up. So as x goes to infinity, y goes to infinity. As x goes to -infinity, y still goes to infinity. So that's up and up. Because of this degree of 3 on that 0, if we think back to the warm-up on page 35, that was a point of inflection where the concavity changes. So we're going to make this, and I'm exaggerating, kind of curvy here, except I missed my x-intercept. There we go. And then turn back around and intersect over there at x equals 2. So because this is a repeated, this -1 is really 3 zeros because of the to the third power, we get this curvy part instead of going straight through when the 0 was only used once. It goes straight through. Okay, for 9, 10, and 11, we are going to do the same. Well, let's just start with 9 and 10. 11's kind of unique because of that trinomial at the end. So we're going to pause the video. We want you to try 9 and 10. We'll give you about 5 or 6 minutes. Okay, for number 9, the degree is 5 because we've got 3, 1, and 1 for a total of 5. Then the zeros are -1, 2, and 1. To make this easier to graph, I'm actually going to go by every block is a half, and I'm going to zoom in. Whoop. That's so nice on the iPad. Okay, -1, -2, -3. Then I'll do +1, +2, +3. It's okay if when you were graphing these, when the video was paused, if you didn't do a scale of 2, that just makes it a little nicer over here where we have the zeros right next to each other. So for end behavior, as x goes to infinity, y is going to go to positive infinity, and as x goes to negative infinity, y goes to negative infinity. So that's going to be up this way and down this way. So if we look at the 0 with the factor with an exponent of 3, that gave me the -1, 0. So I know that's going to be the spot that changes concavity. The other 2 zeros are only used once, so I'm going to intersect the x-axis and just go straight through. It does not matter for our purposes how high and how low the maximum and minimum are being graphed. That part's just a sketch. If anything, when we give you these questions on the exit ticket on, what day is that? Thursday. If you're going to be absent Thursday because it's close to winter break, make arrangements to take the exit ticket before you leave for winter break. But we're just going to give you an x-axis and a y-axis and not a grid, because the grid locks you in because we don't really know how high or how low this maximum and minimum point go. What we care about is the x-intercepts, your end behavior, and the curvature of your graph. So this point of inflection where it changes concavity, or these points where they just intersect the graph. Okay, let's do 10. The degree is 5, again, and this time we only have 2 different x-intercepts of -1 and 2. I'm going to do a double scale again, -1, -2. So we've got -1 as an x-intercept and +2. And for end behavior, it's actually the same as number 9. To the right, we go to infinity. To the left, we're going to go to negative infinity. So that's this way and this way. So to get our graph, we see that this -1 root has a power of 3. So that's going to be the change in concavity. But then to be able to end in the up infinity end behavior, I can't intersect the graph here at 2, of the x-axis at 2. I'm going to have to make my graph tangent so that the end behavior goes up to infinity. That fits with what we saw in the warm-up. Because this is a factor has an exponent of 2, we're tangent on the x-axis. So I'm going to add one more vocabulary word in here before we do 11. The exponent on the factors is called multiplicity. So we would say that the 0, let me get my pointer, sorry. This 0 of -1 has a multiplicity of 3. This 0 of 2 has a multiplicity of 1. This -1, 0 has a multiplicity of 3. This 2, 0 has a multiplicity of 2. So we use those exponents with the word multiplicity to be able to describe what's going to happen on the x-axis as far as the shape of the graph. Okay, so we haven't attempted 11 yet, so let's do 11. The degree of the polynomial, this one's a little more unique than the other 10 problems we've already looked at. Inside our factor, we still have that exponent of 1, so we've been counting the multiplicity exponent for our degree. But now this factor has a degree of 2 and a multiplicity of 1. So when we get our total degree of the polynomial, it's still going to be 5, because we're going to add this 3 and this 2. Now for the zeros, the first factor has a 0 at -1. That one's pretty straightforward to solve. But let's see what happens when we try to solve the other factor. Does that factor factor? Does anything multiply to 1 that adds to 1? No. I'm not going to want to complete the square because this is odd. So let's do a quick quadratic formula. (b plus or minus the square root of b squared minus 4ac all over 2a. Now look what happens here with this discriminant. It's going to be a negative number. It's going to be the square root of -3. So this has non-real solutions. So we're not going to see those in the zeros on our graph. They're not going to show as x-intercepts. So we're not going to list any other zeros. For end behavior, sorry, that's a sloppy arrow. It's an odd degree with a positive leading coefficient. So to the right is infinity and to the left is negative infinity. Here's my x-intercept. We're going to go up and down. And because of this multiplicity of 3, we're going to change concavity at that 0. What you should not do is draw your graph straight through the x-axis like that. That is a multiplicity of 1. When you have a multiplicity of 3, you have to have this curvy part where you change concavity. Okay, on the next page we are going to summarize everything we've discussed. Number 13 says, based on all of our work, let's discuss the relationship between the degree of a polynomial and the number of zeros. There is something called the fundamental theorem of algebra. I'm going to type the fundamental, the theorem of algebra. So look back at our 12 graphs. So we'll pause the video for a moment for you to count how many zeros and how that relates to the degree. Okay, so the degree of the polynomial is equal to the number of zeros or roots, whatever vocab word you prefer, including the complex and multiple roots. So I can't flip backwards in this app, but I'm using to make the video. But you turn back and look at number 5. The degree is 2, and we have an unique 0 at -1 and 1 0 at 2. But if you look at number 6, the degree is 3. Well, the 0 at -1 is counted twice because of the multiplicity of 2. So that's 2 zeros plus the 0 at 2, so that makes 3 total, which is the degree. If you look at number 7, the -1 is counted 3 times because it has a multiplicity of 3. So that's 3 zeros plus 1 more at the x equals 2 for a total of 4, which is the degree of 4. So the fundamental theorem of algebra says the degree of the polynomial is equal to the total number of zeros or roots that a graph will have. But you have to include the imaginary ones. So if you look at number 11, we had a multiplicity of 3 for the -1. But when you solve for the complex zeros, because of the trinomial, remember it would be plus or minus the I root 3. So that's 2 more zeros, or 2 more roots, even though they're complex, for a total of 5. Okay, so let's continue with number 14 and 15. So the exponent of a factor of a polynomial is called the multiplicity. So we've discussed that. Here is the official definition. For example, in y equals x plus 1 to the third, this -1 is a 0 and it has a multiplicity of 3, which means a triple root. A multiplicity of 2 is called a double root. How does the multiplicity of the 0 impact the graph of the polynomial? Okay, so when we had a double root, I'm going to type again. Okay, so when we had a double root, which was a multiplicity of 3, I'm sorry, of 2, excuse me, of 2. A double root is a multiplicity of 2. We know that the graph was tangent at the x-axis, like the x squared. Whoa, where'd that go? Uh-oh. Oh, there it is. Okay, when we had a triple root, or a multiplicity of 3, we had a change in concavity on the x-axis. And then lastly, for a single root, or a multiplicity of 1, our graph just crossed or intersected the x-axis. Okay, and I'm going to draw you a few pictures. It'll make it easier to understand. So the double multiplicity was tangent, where we just skimmed the x-axis. I missed it. That's a little better. So that's a multiplicity of 2. That's the double root. The triple root was the change in concavity, and for some reason I can't, oh, I got a better idea. Where our graph changes curvature, and so this would be the triple root. And then lastly, the single root, it just crosses the x-axis straight through. Okay, if a polynomial is written in the form, oh no. Okay, I fixed that. For 15, if a polynomial is written in the form y equals a times x minus b to the n times x minus c to the m times x minus d to the p, where a is not 0, n, m, and p are all positive integers, write the degree, zeros, and end behavior. Okay. So we're not going to do end behavior. Let's just do the degree and the zeros. We're going to pause the video here for 1 minute for you to figure out the degree and the zeros. So the degree, you should have said, is n plus m plus p, where you add up those multiplicities. And the zeros are going to be b, c, and d, when each factor equals 0. So you could solve this. That's how we get x equals b, and c, and d. So let's do one more example, something like I was speaking about before, where we won't be given a grid, so it'll make the problem nicer. Let's do y equals x plus 5, x plus 1 squared, and x minus 2 to the third. And I just want to graph it. So we're going to pause the video. I'll give you 3 minutes to sketch a graph of that, and then I will show you how I'm going to do my answer. Okay, so I know my first root is at -5, my next root is at -1, and my last root is at 2. So see how without a grid, it kind of just makes it nicer. I can space them far enough apart so that it's legible. And then my degree overall is 6, which is even. So I know the end behaviors of my graph are going to go up and up. And now with the multiplicities, x plus 5 has a multiplicity of 1. So I know when I go to graph that x-intercept, I'm going to intersect the x-axis. X minus 1 has a multiplicity of 2, so I'm just going to be tangent there. And then at x minus 2, which gives me the 0 of 2, I'm going to have a point of inflection or a change in concavity because of the multiplicity of 3, and both ends go up. Okay, now we're going to start your homework. Your homework is page 41, numbers 1 to 13. Use the rest of the class period to start that and maybe get it done.